10 gemstones that predict future disasters. Some disasters strike without warning. Others leave a record, not in prophecy, not in symbols, but in minerals, crystals, and buried signals that were never meant to be decorative. Across the world, geologists are decoding physical materials that don't just preserve the past, but actively define how we understand the future. These are not mystical stones. They are timestamps. Some formed in the seconds after a meteorite impact. Others grew for millennia in volcanic magma, absorbing stress, heat, and radiation like a slow geological memory. And some, like coral, quartz, or cave calcite, respond to the world around them so precisely they record earthquakes, sea level shifts, even tsunamis, without a single human witness. But why does it matter now? Because many of these materials are being used, right now, to model real-world risk. Not in theory, not in simulation, but in live frameworks that estimate the probability of future eruptions, fault ruptures, and planetary-scale events. The crystals are not warning us, but the data inside them is. In this film, we're not looking for omens. We're reading physical records, stone by stone, across 10 extraordinary minerals that help define what disasters are likely to happen again, and possibly how soon. Don't forget to press and hold that like button, leave a comment, and hit subscribe before we begin. Ranked 10th, Darwin Glass. Earth's Forgotten Impact Warning. Not all gemstones are shaped by time. Some are created in an instant. In the remote southwest of Tasmania, beneath a canopy of rainforest and sediment, scientists discovered a strange natural glass scattered across the landscape. It wasn't beautiful. It wasn't valuable. But it carried evidence of an event no other material could preserve. This is Darwin Glass, the result of a high-velocity meteorite impact that struck Earth approximately 800,000 years ago. When the object collided with the ground at more than 15 kilometers per second, the energy release vaporized the bedrock, launching molten debris into the air. As that material cooled mid-flight, it solidified into glass. What remains today is a field of irregular fragments, unpolished, translucent, and fused with trace elements from the blast site. For years, Darwin Glass was overlooked as an oddity, but then came the isotopic data. Using argon-40/argon-39 laser dating, researchers pinpointed its age with remarkable precision. The material's chemical signature and spatial distribution allowed geologists to reconstruct the whole geometry of the impact, from directionality and crater spread to kinetic yield. More importantly, Darwin Glass became a control sample for understanding how regional meteorite impacts behave in real environments. That data now feeds into global risk models, the kind used by NASA, ESA, and impact forecasting labs to estimate the likelihood of future airbursts or crater-forming collisions. Unlike early warning systems or satellite surveillance, Darwin Glass offers no live alert. What it provides is long-term calibration, a way to measure the quiet intervals between impact events and to assess how violent those returns might be. In a field where prediction often relies on simulations, this glass remains physical proof, a forensic timestamp of planetary violence, and a necessary data point in the ongoing attempt to model what might come next. Ranked 9th, Libyan desert glass, what survived an airburst without a crater. A thin crust of fused glass lies scattered across one of the driest regions on Earth. Libyan desert glass, pale yellow, high silica, and chemically pristine, is unlike any natural glass formed by volcanoes or lightning. Its temperature of origin exceeds 1,600 degrees Celsius, a threshold no surface process on Earth can reach under normal conditions. Geologists now agree, this material was formed by an astronomical event. The shock signatures within it, including Le Chatelierite veins and baddelite from shock zircon, confirm the input of extreme energy, likely from a meteorite airburst that vaporized rock and sand over a wide radius, then cooled rapidly in the desert air. Its age, measured at roughly 29 million years, predates written history. Yet it did not go unnoticed by ancient civilizations. A carved scarab made from Libyan desert glass was set into the funerary pendant worn by the pharaoh Tutankhamun. not as a gemstone of wealth, but as a symbol possibly tied to cosmic power. Despite the absence of records explaining its significance, the artifact itself survived intact, quietly linking an ancient ritual to a long-forgotten celestial explosion. Today, Libyan desert glass is more than a relic. It is a working dataset, a terrestrial result of an atmospheric impact significant enough to leave no crater, but powerful enough to alter the mineral record. Scientists use it to model high-energy airbursts, similar to the Tunguska event in Siberia or the Chelyabinsk explosion over Russia. It provides a scale reference for the potential heat, shockwave pressure, and glass formation associated with subcrater impacts, scenarios which remain critically understudied in planetary risk assessments. The value of Libyan desert glass lies not in its clarity or cut, but in what it quietly preserves: a physical record of thermal violence, formed without warning, under conditions that could be repeated, not in millennia, but potentially within modern memory. Ranked 8th, Moldavite, 300 kilometers from the crater, but still part of the impact. Across a vast stretch of Central Europe, embedded in soil beneath fields and forests, lies a strange green glass that doesn't belong. Moldavite. It's not volcanic. It didn't cool from any known eruption, and no known lightning strike has ever fused Earth into this form. For decades, its origin was a mystery, until researchers connected the dots. More than 15 million years ago, a meteorite roughly a kilometer wide struck what is now southern Germany, forming what we know today as the Reese crater. But the crater wasn't the only outcome. The impact released enough energy to vaporize part of the Earth's crust, ejecting molten silicate material into the upper atmosphere. That material cooled mid-air into irregular droplets of glass and fell in a wide arc over 300 kilometers away, across what is now the Czech Republic. What we call Moldavite today is the result of that one singular trajectory. But this isn't just a historical curiosity. Moldavite is unique among terrestrial materials. It's the only tektite with a precisely identified parent crater in a fully map-strewn field. The distribution of fragments, their size, composition, and even their orientation in sediment layers allows scientists to reverse engineer nearly every aspect of the impact event. They've used Moldavite to estimate the velocity vector of the ejecta, the angle of atmospheric entry, the height and shape of the impact plume, and the thermal load that allowed the glass to harden without crystallizing. In a world where future airburst events like Tunguska or Chelyabinsk remain difficult to model, Moldavite provides a baseline, physical evidence of what planetary-scale kinetic violence looks like when it doesn't leave a clear crater. Its value today is often misunderstood. In commercial markets, Moldavite is sold as a healing stone, a spiritual talisman, or a gemstone with extraterrestrial resonance. But in scientific terms, its power lies elsewhere. This glass doesn't predict the future by superstition. It does so through physics. It captures the raw signature of how far and how fast devastation can travel from a single point of origin. For planetary defense strategists, it offers one of the few Earth-based data sets available to simulate not only direct impacts, but their far-reaching consequences. It helps define how airbursts fragment, where debris might fall, and the distances between the source and the fallout. To hold Moldavite is not to touch something magical. It's to have material proof of energy released on a scale we rarely witness and barely understand, and to recognize that similar trajectories could be repeating themselves unseen even now. Ranked 7th, Speleothem Calcite, earthquake history, trapped in broken growth. A clean vertical growth, paused, a shift in alignment, a fracture that doesn't follow the pattern of mineral deposition. These are not decorative features, they are impact records. Inside cave systems around the world, speleothems, slow-growing columns of calcite deposited from dripping groundwater, have quietly recorded movements of the Earth that no human ever witnessed. When a fault line ruptures underground, even without breaking the surface, the resulting ground motion may shear or deform these formations. Some snap cleanly, others freeze in place, and in many cases, their internal structure reveals sudden shifts in water chemistry or growth orientation that correspond to seismic stress. This isn't speculation. Using uranium-thorium dating, Scientists can determine precisely when these shifts occurred, sometimes with precision down to a few hundred years. In areas without historical records or surface ruptures, speleothems provide one of the only means of reconstructing earthquake recurrence intervals. Known as speleoseismology, this technique has redefined paleoseismic research in regions from the Eastern Alps to central China. It's allowed researchers to identify previously unknown seismic zones, calculate return periods of large magnitude events, and even assess whether current building codes underestimate local risk. Speleothems don't look dramatic, but they serve a rare function: physical record-keeping of ground instability in 3 dimensions. In caves where nothing is written, they are the only data that persists across millennia. And in hazard modeling, their fractured timelines are being read not for their beauty, but for what they say about what comes next. Ranked 6th, coral microatolls, sea-level earthquake records you can still measure. Growth halted at the top, shifted sideways, and began again, but lower. Along certain Pacific coastlines, this pattern in living coral isn't random. It's a timestamp. Microatolls, disc-shaped coral colonies limited by the lowest sea level they can survive in, form a flat upper surface that tracks the tidal minimum over decades. But when an undersea earthquake lifts or drops the seafloor by even a few centimeters, the surrounding water depth changes instantly. The coral reacts. Its upper rim dies off where exposed, and a new growth band begins at the corrected elevation. That interruption remains visible, even centuries later, in the form of dead coral scars and horizontal growth resets. These aren't simply biological curiosities. In regions like Sumatra, Simeulue, and the Mentawai Islands, microatolls have preserved a record of major subduction earthquakes going back hundreds of years. Long before seismographs or written logs existed, scientists working with coral records in the late 1990s used them to reconstruct the recurrence intervals of magnitude 8 and 9 earthquakes across the Sunda Trench. The patterns they found: uplift in 1833, subsidence in 1861, quiescence for over a century, pointed directly to the risk of a significant release. When the Indian Ocean earthquake and tsunami struck in December 2004, the warning had already been encoded in coral. Unlike satellites or deep ocean sensors, microatolls don't require maintenance or funding. They're passive instruments, living, growing, and storing spatial data with biological precision. Where no data exists on paper, coral builds the record, quietly year after year, until someone reads what tectonics has written beneath the sea. Ranked 5th, Obsidian and Tephra, eruption records that define future risk. Not every warning leaves behind a siren. Sometimes it leaves a layer. Across volcanic zones around the world, bands of compressed ash and welded glass sit buried beneath modern soil, marking moments in Earth's history when magma reached the surface with catastrophic force. These layers, composed of tephra and obsidian, are not random. They're precise records of eruptions, each encoded with grain size, chemical fingerprint, and datable isotopes that allow scientists to reconstruct the timing, scale, and frequency of past events. Obsidian forms when high silica magma cools rapidly without crystallizing, often at the final stages of explosive eruptions. It may appear sharp, dark, and inert, but when found in a stratified context, layered among pumice, ash, and pyroclastic flows, it becomes part of a timeline. Tephrochronology, the study of volcanic ash layers, has enabled researchers to correlate eruptions across regions, identify periods of dormancy, and build models of volcanic behavior not over decades, but across tens of thousands of years. In the Long Valley caldera, for example, the sequence of obsidian domes and tephra beds tells a story of repeated dome-building phases, punctuated by caldera-wide eruptions. At Taupo in New Zealand, the distribution of tephra deposits across the Pacific has helped define one of the most explosive volcanic systems on Earth. And in Campi Flegrei, the depth and spread of past tephra layers have become central to risk models estimating the probability of reactivation beneath a densely populated region. None of these materials signals when the next eruption will occur. but they form the statistical bedrock on which modern hazard assessments are built. By measuring how long it has been since each layer was formed and how consistently eruptions have repeated in the past, volcanologists can calculate conditional probabilities. Not prophecy, but likelihood. And in a field where minutes matter, Obsidian and Tephra remain the most enduring archives of what happens when pressure can no longer be contained. Ranked fourth, Quartz OSL, the light signal that dates past disasters. A single grain of quartz buried in sand absorbs energy from its environment the longer it remains in darkness. When exposed to sunlight, that energy is reset, like clearing a geological stopwatch. But when the grain is buried again, by flood, by tsunami, by shifting earth, the clock begins once more. Decades or even thousands of years later, that grain can be extracted and tested. With a controlled burst of light, it releases its stored energy as luminescence. And from that response, scientists can determine the last time it saw daylight. This is the basis of optically stimulated luminescence dating, or OSL, one of the few tools capable of measuring when a significant event deposited sediment. Unlike radiocarbon dating, OSL doesn't require organic material. Unlike tephrochronology, it doesn't depend on volcanic ash. It works on nothing more than light and sand. That makes it particularly powerful in coastal zones where written records are absent, and where tsunamis or storm surges may have occurred long before modern monitoring began. By analyzing quartz grains in buried beach layers, researchers have used OSL to identify tsunami deposits in Sumatra, Thailand, Chile, and beyond, sometimes revealing that an area previously thought safe has a return period of less than 300 years. This data feeds directly into hazard models that inform zoning, construction standards, and early warning systems. Without it, entire coastlines would still be modeled as low risk. Quartz doesn't warn. It doesn't glow in the dark. But in laboratory conditions, it tells a story that would otherwise remain lost. A story of when the land changed and whether it's likely to change again. Ranked third, Zircon. 300,000 years of waiting, 30 years to erupt. A crystal forms deep underground, not quickly, not explosively, but slowly over time, in the quiet upper chambers of a magma reservoir that hasn't yet made itself known at the surface. It's zircon, a mineral smaller than a grain of sand, yet more geologically articulate than any earthquake, any gas reading, any satellite scan. What it carries isn't danger, but duration. What it stores isn't energy, but time. And in the study of supervolcanoes, time is everything. Zircon begins to crystallize when magma-rich in silica begins to cool, often at the margins of massive, long-lived magma bodies that fuel the world's most significant eruptions. These crystals incorporate uranium atoms as they form, and those atoms begin to decay, ticking like tiny atomic clocks. The transformation from uranium to lead is unchangeable, unaffected by pressure, heat, or chemistry. That stability makes zircon the single most reliable tool for measuring the age of magma systems, especially those that remain hidden for millennia before releasing their pressure in a single, catastrophic moment. But what makes zircon especially valuable is not just its ability to tell when it formed, but how many times it has been remobilized. A single grain can hold zones that crystallize at different periods, reflecting episodes of magma accumulation, recharge, and thermal resetting. This allows scientists to reconstruct the tempo of magma beneath supervolcanoes. In places like Yellowstone, Taupo, or Toba, zircon has revealed that reservoirs capable of erupting at the VEI7 or VEI8 scale are not sudden phenomena. They build slowly, they pulse, they store magma for hundreds of thousands of years, with surface activity so minor it's often invisible until the final decades before eruption. At Yellowstone, studies of zircon grains from the Lava Creek Tuff, the most recent caldera-forming eruption there, 631,000 years ago, have shown that much of the zircon crystallized throughout 100,000 to 300,000 years before the event. But startlingly, many of the outer growth rims, the last layers before eruption, formed just decades before the explosion. In other words, the reservoir mainly sat dormant for hundreds of millennia, then underwent a rapid, late-stage transition into eruptible magma within a single human lifetime. Zircon, with its layered isotopic record, captured that shift long before anything on the surface did. This is what makes zircon irreplaceable in volcanic hazard modeling. It doesn't act as a sensor, it doesn't provide alerts, but by reconstructing the frequency and time scale of past eruptions, down to the century, even the decade, zircon defines the statistical framework on which all long-range eruption forecasts depend. It's not about seeing the future, it's about proving how long it took to get here. Unlike gas monitors or thermal cameras, zircon doesn't lose calibration, and it doesn't drift with funding cycles. It survives embedded in ignimbrite, welded tuff, and rhyolitic domes, ready to be read when a volcanologist drills, samples, dissolves, and measures. In places where supervolcanoes sleep for 500,000 years, zircon is often the only line of evidence we have to tell whether the clock has restarted and how far along it may be. Ranked second, Plagioclase. How volcanoes reveal their countdown clocks. How much time do we have? That's the core question in every volcanic hazard model. Not how big, not where, but when. Plagioclase, a feldspar mineral found in andesite, dacite, and rhyolite magmas, is one of the few materials that can help answer it. Unlike surface sensors or seismic patterns, plagioclase crystals preserve a chemical record of their exposure to heat and fluids. As magma rises and mixes with new injections of molten material, trace elements like strontium, barium, and magnesium begin to diffuse across the crystal's growth zones. That diffusion rate is measurable, and from it, volcanologists can calculate how long the crystal has been in contact with eruptible magma, not in geologic terms, but in human terms. Weeks, days, sometimes hours. At Mount St. Helens in 1980, researchers later analyzed plagioclase from the dacite dome and discovered that diffusion profiles indicated magma mixing just 2 weeks before eruption. At Pinatubo in 1991, the data suggested pre-eruptive activity began about 30 days prior. And at Soufriere Hills in Montserrat, a pattern of increasingly short pre-eruptive mixing intervals allowed scientists to calibrate their forecasts in near real time. This level of resolution would be impossible without crystal chronometry, a method that treats plagioclase not just as a mineral, but as a time-stamping tool forged inside magma chambers. Plagioclase doesn't show stress cracks or thermal pulses at the surface. It doesn't release gas or trigger harmonic tremor, but when dissolved and analyzed in thin section, it tells a precise story of how long magma has been preparing to erupt. Combined with GPS deformation, seismic swarms, and degassing data, it helps transform vague warnings into actionable forecasts. In a field where decision-makers must choose whether to evacuate 100,000 people and whether to do it today or wait one more week, plagioclase is more than a rock. It is one of the only internal records of how fast magma systems accelerate and how little time there may be before the surface breaks. In first place, Olivine, the only crystal that tracks eruption time in days. No other crystal records the countdown to an eruption in days, except Olivine. Formed in the earliest stages of magma cooling, Olivine incorporates magnesium and iron into its structure based on temperature, pressure, and chemical environment. When a new pulse of magma rises from depth and mixes with an existing reservoir, those elements begin to redistribute almost immediately, and the gradients they leave behind inside the crystal, between core and rim, between fast cooling and slow reacting zones, act as microclocks. When analyzed with high-resolution electron microprobes, these diffusion zones reveal the time that has passed since the last mixing event. In some cases, that time is less than a week. This isn't theoretical, it's been demonstrated repeatedly in active volcanoes. At Eyjafjallajökull in Iceland, olivine crystals indicated that magma mixing began just 3 to 7 days before the 2010 eruption. At Kilauea, in multiple events since 2018, olivine revealed mixing intervals of fewer than 5 days. In Galapagos, similar results were found in submarine basaltic systems. These are not long-term hazard assessments. They are real-time forensics, helping volcanologists interpret seismic and gas data not as vague alerts, but as signs tied to measurable internal movement. Olivine's crystalline record doesn't change with pressure. It doesn't reset in storage. Its diffusion patterns lock in from the moment of chemical imbalance. That makes it more than a mineral. It is a timestamp embedded directly inside the material that rises to the surface in eruptions. And when those patterns are scanned, they can refine eruption forecasts from months to weeks, even to days. Peridot, the gem quality variant of olivine, is often cut, polished, and worn for its color. But the unpolished crystals collected near vents, domes, and lava lakes are different. They are not decorative, they are functional. They are the only materials capable of telling us, with quantitative precision, how close magma is to breaching the surface. In volcanic systems where ascent rates can shift from kilometers per day to eruption in under a week, olivine is not a warning, it is a clock, buried, preserved, and waiting to be read before it's too late. They're not diamonds, not rubies, not even what most people would call gemstones. But each of these minerals, melted by meteors, forged beneath glaciers, or born from nuclear-level tectonic pressure, holds something no luxury boutique can replicate. Proof that Earth once screamed. We chase these stones not for their sparkle, but for the ancient violence still trapped inside them. Because sometimes the most extraordinary jewels aren't cut, faceted, or polished. They're witnesses. And those who learn to read them don't just collect beauty, they collect truth.